Bismillah ar-Rahman ar-Rahim. Assalamu alaikum again. Thank you for coming, and please bear with me. Tonight is the last night, and hopefully, inshallah, we will be finishing with all the material. So please bear with me. So yesterday we talked about, we're still in the analyze phase. We talked about hypothesis testing. And we showed a few examples, and now I would like to show you a roadmap for doing hypothesis testing. And when you go to the exam, I think you should have a map like this. You need to have a map like this, because there will be questions about what hypothesis testing you will be using when you're dealing with various situations. So this is a hypothesis testing for the averages. Let's say you have an average and you want to compare it. You want to make a conclusion out of that sample that you collected. So basically you start here. You start here and say you want to compare the averages of some sample of the data, and you want to decide if they are statistically different or not different. You have two samples, for example, and you want to see if this sample is different. Is Muhammad performing different than Ahmed, for example? So you take data from Ahmed and you take data from product A and product B, and you want to do the comparison. So you enter it here. So you ask your question, the first question. Are the samples normally distributed? And by the way, most of the softwares, there is a test for normality test. You can actually just give it the software, give it to the software, and the software will tell you if the data fits a normal distribution, as we discussed, or it doesn't fit a normal distribution. And it tells you if you're not sure. Sometimes you're not sure, so you use this test. So basically, all you do, you go to the software like Minitab or Sigma Excel, and you choose Turkey's, Techies quick test, and that's how you do the comparison. If you're sure that it's not normal, then you have either you transform the data, and there are some transformation which is not covered, normally in Greenbelt, or you go to median test. Instead of testing for averages, if their averages is different, then you say, no, I don't think it's a good idea. Maybe I'll compare the medians and say, and then median are good comparison as well. You want to see, are they different in median? Then that's a comparison. But if it is normally distributed, yes, then it depends on how many samples you want to compare. If you want to compare only one sample to a historical mean, then you want to use the one sample t-test. And all you do, basically, you go to the software and you select one sample t-test, and it's usually from a drop-down menu. Like in Minitab, it's from a drop-down menu. So you go and select it. And you give it like we did before. This is actually, this is a sample t-test. You give it the data, it will give you a screen like this one here. You give it the sample size, you give it the mean, you give it the standard deviation, and you give it what you want to compare the sample to. And it will give you the analysis as we discussed last night. So that's what you do. So that's if it's one. Sometimes you're not comparing to a historical mean. It's not like the mean and you want to see if it has shifted or not. You want to compare two samples together. If you want to do two samples together, then you use two sample t-test. Or you could use the pair t-test. So it's not an optional thing. It depends on the situation. As we said, last night, a pair t-test is you want to compare each one with its pair. Like, for example, if you want to see if the husbands are older than wives, for example, you don't want to use two sample t-test, because two sample t-test will test all the women together with all the men together. So you'll maybe women live longer, so you'll see them older. But what you want to do, you want to do a pair t-test. So each husband with his wife, that's a pair t-test. If the two samples are unknown, if the samples are more than 2, then you use the one-way ANOVA. So that's for 3 or more. So basically, it's very simple. You just put your data in the software normally in columns, and you just tell it, okay, I want to do a one-way ANOVA, for example. And what's ANOVA? Does anybody remember what ANOVA stands for?
Analysis of variance.
Exactly, it's analysis of variance. And the variance is the square of the standard deviation. As you remember, when we calculated the standard deviation, we calculated it, you know, we calculated the variance, and then we took the square root of the variance to get the to get the standard deviation. Perfect. In situations where you cannot, normally it is safe to assume normal distribution. In exams, if it's not given, then assume it's normal distribution. That would be a safe assumption. Another thing, in software like Minitab, press help. If you press help, it will give you like a full tutorial about what is one sample t-test or what is two sample t-test and so on, and it will give you even exercises, and if you purchase the software, it will give you data to experiment with and so on, and that's how you learn. And you'll get a screen like this. You get an overview, you get a how-to, you get an example, you get some data and so on, and how you interpret the data. So Minitab is not just an analysis software, it is also like an educational software, actually, because you can't remember everything. You know, when you're dealing with a problem, you want a refresher, and software like Minitab and Sigma Excel are good refresher. You could go and you could see example and so on. So that's comparison of the means. The same thing here. If you want to do comparison of the medians, sometimes you want to see, is the median salary of a group A is different than the median salary of a group B? Is it the median salary is in a certain country different than in another country, in America versus Canada, and so on? Whatever, you know. Sometimes you want to analyze the median, you don't want to analyze the averages. And it's the same, basically same route map, same route. You start here, you say you want to compare the medians for some data. So you want to say, are the data or the samples normally distributed? If they are normally distributed, don't forget that you can also compare the average, because normally if they are normally distributed, normally the preferences you compare the averages, but it depends on your situation. But if they are not normally distributed, then you just ask the same questions. How many samples? So if it's only one sample compared to a historic median, then you're gonna do a one sample sign test. So the one sample t-test basically is similar to what? And the mean, it's similar to the one sample t-test. So the one sample t-test is for the averages or for the means and statistics, and for the medians, it's the one sample sign test. If they are two or more, then if yes, then you want to use this test basically. And they're all just different tests. You just tell them that I want to do this test or I want to do this test. So if they are there any obvious, if there are two or more, then you're going to ask this a question: are there any obvious outliers in the samples? If yes, if you've seen outliers, and remember the box plot and the whiskers and so on. So if you see any obvious outliers, then maybe you want to use the Moore's median test. If not, then maybe you want to use the Kruskal-Wallis test. So basically, it's a route map. And again, many people think that hypothesis testing is really a very difficult concept. It's not. It's not a difficult concept. It's basically you have a mean and you have a standard error, And if you have a mean and a standard error, then you have a confidence interval. You say, my data has to be between this and this. I'm 95% confident, or I'm 99% confident, but that's the concept, and this is the method to do it. If you decide, no, you don't want to compare the means, you don't want to compare the median, but you want to compare the standard deviations. And why do you want to compare the standard deviation? You want to see if there is so much variation, because Six Sigma is all about variations, you know. Is this the variation of sample A higher than the variation of sample B? Then that's, again, very simple route for it. Are the samples normally distributed? If yes, then you go this way. If no, then you go Levine test. If yes, then if there are two samples, then use the F-test. If 3 or more, then use the Bartlett test, basically. It's a pretty straightforward. This is test for proportions. You want to test proportions. You want to say, let's say you take percentages, and you want to compare two percentages, and you want to see if they are different or not different. You know, are they coming from the same distributions, or are they coming from different distributions? So, but that's what you do. This is very, very, very straightforward. Either use one proportion test if it's only one sample against a target value. Say, am I below 80% or am I above 80%? Let's say you get 70%. You want to make sure, am I confident that this is not just random, you know, or is it only the sample? Because you can't be sure without doing a hypothesis testing. So what you do, you have the sample size. Of course, the higher the sample size, the more confident you are in the data. So you take the sample size, you use the formula, you know, or you use the software here. You just use one proportion test, and it will tell you that you get, let's say you're targeting 80%. Now your sample says 75. Are you sure that this 75 is really lower than 80%? You're not sure. Maybe it's just random sample. You just something by random took it, and that's it. So this is how you do it. Or you took two samples from class A and class B, and then you find out that the proportion of these people is 80%. These one are 82%. Is 80% really different than 82%? No, you can't. Maybe it's just a sample that you took. So it's if there are 3 or more, then use the chi-square test. So chi-square test normally, you know, you could get questions like this in the exam. It's for categorical, you know, because it's like you're categorizing. A proportion is more of category type of thing. So it's for pass, fail, things like this. So it's yes, no, and so on. So that's you know. So chi-square test is related to categorization things and so on. So that's about hypothesis testing. The last point that I would like to cover in hypothesis testing is the type 1 and type 2 errors. I'm sure many of you have heard errors, because there is an error. There is always an error. You make an assumption and you say, I want to be 95% confident. Then there is 5% confidence, you know, there is a 5% risk that you're getting it wrong, right? Because that's what it means. If you use an alpha of 0.05, you're accepting alpha. That means you're accepting an error of that much. So that's what it is. In medicine, I think they use alpha equal to 0.01. They're more strict. And manufacturing, engineering, and so on, alpha 0.05 is acceptable. So here are the basically the errors. You put the null hypothesis. And if you don't reject the null, if the null hypothesis is true, you know, this is your assumption, your basic assumption. If it is in reality, it is true, and you did not reject it from your sample, your analysis did not reject it, then yeah, good. Then you guessed it right. So you are here now, basically, you're right, there is no error. But there is a possibility that you say my null hypothesis is true when it's not really true, basically, and you reject it. If you reject it, you know, if it's true and you reject it, then this is called a false positive error. And it's called also type 1 error. It's just like if I want to compare it to, you say, well, all innocents are, offendants maybe are innocent, كل المتهمين المتهم بريء, okay? So it's either you accuse him and then it's a mistake, or he can be innocent and you say he is guilty. So either way, there is a possibility that you could make a mistake. It's the same thing here. So you start with a null hypothesis. You say this is equal, and if it is really true, it's equal. But you don't reject it. Then this is true. You didn't make a mistake. If you reject it, then it's a false positive. But in the other side, if it's false, if the null hypothesis is false, but you rejected it, you didn't like the null hypothesis, or you didn't reject it, then it's a false negative. It's a simple concept. Just look at it again. It's either you say something and it turns out to be the opposite. That's what it is. That's what's type 1 error, type 2 error, and type 1 error is false. Type 1 error is false negative, and type 2 error is type 1 error is false positive, and type 2 error is false negative. Is this clear? Did I confuse you? I feel that I probably have confused some of you. Are you? And anybody still confused?
Confused. If you can have some other simple example for this.
Okay.
Practical example, if possible.
Yes. Let's say that the actual mean that we don't know is 100. We don't know it's 100, but in reality, Allah knows that it's 100. Okay. And we take a sample, and we see that it is 95. And based on this, we say, yeah, I think we are. We make a decision. We say it's 100. So there is an error, okay? Because you say it's close to 100, so it must be 100. So there is an error here. Or we don't say it's 100, and there is an error also. So either you say it is, and it turns out to be it is not, or you say it is not, and it turned out to be it is. So that's what it is. There are two types of error. Just like the guilty and the innocent. I don't know in reality if he is guilty or if he's innocent. So if I say he is guilty when he is really innocent, then that's an error. And if I say he's an innocent when he's actually guilty, that's an error also, right? So, but this error is type 1 error, and this error is type 2 error. So if the null hypothesis in reality that we don't know now, if the null hypothesis is actually true, okay, but we don't reject the null hypothesis, then we're making the right conclusion. But if the null hypothesis is true and we reject it, then we're actually making a type 1 error, which is a false positive. At the same time, if the null hypothesis is false, okay, and we don't reject it, then we are making an error, and this error is called false negative. But if it's really false and we reject it, then we're making the correct decision here. So that's the concept. I think if you think about it later on, you will figure it out.
Thank you. It was made quite clear. Thank you so much.
Thank you. So that's type 1 error and type 2 error. You want to know that type 1 error type 1 error is a false negative, and type 2 error is a type 1 error is a false positive, and type 2 error is a false negative, and it's in this thing here. Okay, very good. Now, I want to move into another subject within the analyze, which is the correlation. Let's say you collected sample data, and these are different people. Let's say somebody with a height of 46 centimeters, you've seen his weight to be 75. And so on. Number 2, this is his height, and this is his weight. Number 3, and so on. And you collected a few data. What conclusions can you make out of these two columns? Can you see any relation between the two? It is difficult actually to see without doing correlation analysis or some artificial intelligence to this. It is actually difficult to tell. So correlation, basically trying to build to give you a relation between this number and this number, and the correlation is either a positive correlation or a negative correlation. A positive correlation, it means that the more height, or the taller the person, maybe the heavier he is. So this is called a positive. There are other correlation where when one variable goes up, the other variable goes down, and this is called a negative correlation. So here, what you need to do is basically you plot the height in your x-axis, and you plot the weight in your y-axis, and you can see just by plotting them, you can see that there is a trend up. So you can actually see that the weight is actually correlated to the height. So the higher the weight, or the higher the height, is actually the higher the weight. So that's you can see it is correlated. So by plotting them, you can see that there is a correlation. But better if you can fit a line here. If you fit a line, you can see that the correlation is actually, if you calculate the slope here, and you can see that there is actually a 0.86 correlation. So what it means here is that 86% of the variability in the weight is actually can be explained in the variability in the height. The other 14% cannot be explained. So the taller the guy, the heavier he is, but that's only 80% of the variability is being explained by the height, but there are other factors as well. So that's what correlation is. And correlation is very easy. You can do that in Excel. This is the function for correlation. You just select array 1, which is in one column. You select array 2 in another column, and you just type the function correl. And you put the two together, and you get, in here, you get a positive 91 for some of the data. If you get a positive 91, what does that mean? The positive sign means that the relation is they are actually directly related. The higher, one variable, the higher the other variable is. If you get a negative sign, that means it's an inverse relation. The higher one of them, the lower the other. So a 91.91 means that 91% of the variation is explained by the variation. Let's say it's by variation vibration, maybe explained by variation in temperature, for example, the other variable. So that's what it means. So that's correlation. However, if you have something like this, let's say this is your line, and you don't want just to know if they are correlated or not correlated. You also would like, if you have one variable, you would like to be able to guess the other variable. So you go from correlation to the concept of regression. Regression is basically drawing the line and also coming up with an equation for that line. So you're coming up with an equation of y in terms of x in this case. So that's it. So let's say, for example, you have a weight of 140 centimeter. Can we estimate the way, if we have the height, sorry, if they have the height, 140 centimeter, then we should be able to actually calculate the weight. How do we do it? We actually come up with the equation for this. And if you use a software, where are we now? Yeah. If you use a software using for example, the method of least square, you could get an equation here. So that's basically the weight in terms of the height. So if you have a height of 140 centimeters, you multiply it by 0.89. That's the equation that we got. And there is this is called the y-intercept. You subtract this value and you could get the weight. Basically, what regression will do, will give you an equation. It will give you y equal intercept plus mx or something like this. Okay, so it's an equation basically. It gives you, so you and instead of just in correlation, it just tells you if they're related or not related. But here it actually gives you an estimation. If you have one variable, it will estimate for you the other variable. Is that clear? If you use a software, then you need to look at some data here. You need to look at the R square, something called the R square. And the R square, you want to get something 90%, 85%, because this tells you how good the fitness of the curve. If you get a poor number here, then maybe there's a problem with the fit. Maybe you fitted the wrong line. Again, also you want to look at the p-value. The p-value is very important. So, and again here, you want to get low p-values. If you get low p-values, that means that your model is good model and you can use it. But if you don't get good, good p-value, if your p is higher than 0.05, that's the norm, then you say, no, I don't know if I can actually use this model. If I don't know if I can use this equation, because this equation probably doesn't fit the data. So that's very important thing here. This is called the intercept. And anybody who took algebra, or geometry, he knows that y is equal to the slope times x plus an intercept. So this is the intercept, and this is actually the coefficient here. This value is the coefficient. So it's this value times the height plus an intercept. And you could use the formula as this formula. Any height that you have, you could just actually plug it into this formula and you will get a weight for it. And this is called regression. Something very important in regression are the residuals, because there is no perfect fit, never, unless it's really a pure physics, then something. In statistics, normally there isn't a pure fit. And there is a saying, they say all models are wrong, some are useful. So whatever model you come up with, at the end, there is some errors. And in regression, these errors are called residuals, and you want to get the residuals. So you fitted, some of the data has fit, but there are some residuals. And the way you look at them through a histogram and a probability plot. I'm not going to go into details of this, but these are, are actually methods to evaluate the goodness of your regression model. So you put a regression model, you have an independent variable, which is the y, and you have dependent variable, which is the x. And so you want to see how the model fits, the equation that you came up with, how does it fit? Does it fit very well, or it doesn't fit very well? There is also multiple regression, because y can be a factor, and that's normally the situation. There are a number of factors that affects the situation. So y can actually be can be a function of many x's basically. So this is called multiple regression. In this example here, let's say y is your orthodontic treatment need, whether you need it or not, and it depends basically in factors like this, maybe 10 factors or something. And you want to see if there is really a relation between the orthodontic need and between these factors. So what you do regression, you take it. So these are your factors, basically some dentists know what they are. But again, it's the same as single regression, multiple regression in terms of analysis. What you do, you still look at the R square, very important. You look at the P data, and you look at your equation, whatever that equation is, if it's a long equation. But very important thing here, in multiple regression, normally you miss interaction effect. Because sometimes if you have an output that is a function of more than one input, sometimes it's not, there is an interaction effect between the variables. So it's only when two, let's say y is a function of x1 and a function of x2 and a function of x3. You have three x's. Sometimes there is a relation between y and x, and sometimes there is a relation between y and x2, but sometimes there is a relation between y and x1 and x2 put together, the interaction. Only when they interact with each other, there is. So regression in general, whether multiple regression or not, you know, that does not look at an interaction effect. And this is why you want to look at advanced method like the design of experiment. Are we okay so far? Does anybody want me to repeat something very quick here? I know it's heavy, but it's Dr. Fayaz, are you, because you're my gauge here. Am I confusing people yet?
No, I'm more excited to move on to the next slide shown over there, the design of experiments.
The design of experiment, excellent. Oh, this is an excellent tool. Sometimes they teach it only in a black belt, but they do teach it in green belt. And I think the green belt exam from ILSSI, probably you will see, you know, a general question about design of experiment. But let's take this example and let's see you know what design of experiment is. Let's say like this is a rolling machine. You take an input steel with a certain thickness, and then you roll it to something that is an output thickness, just something thinner. And here are basically the roller. And let's say there are 3 playing factors. These playing factors is the input thickness, of course. How much thickness is the input thickness? And the lubricant type, whether it's type A or type B. And also the roller pressure, how much it is actually pressing. So there are 3 factors. Now I want to know the relation between these factors and my output thickness. And by the way, this example can be in any setup, can be an orthodontic example. Anything, maybe for Dr. Hawra, well, you're a pharmacist, okay? And you want to see what is the best mixture of things that will give me the right output, the right thickness, the right whatever, the right whatever it is, ppm, anything. So I want to adjust these factors so that it will give me the best value. Now, if we want to do trial and error, how many trial do we need? The temperature is between 800 and 900. That's the range. So how many are there? If I'm going to try every degree, already there are
100 trials.
What?
100.
100, of course. And the pressure between 1500 and 1750, you have around 250.
Okay.
And,
Yes.
and the lubricants you have to, so if you multiply actually these together, did I multiply them or did I not multiply them? Okay. If I multiply these together, then I need 50,000 combinations to try, right? The temperature is 100 combination, the pressure is 250 combinations, and the lubricant is 2 combinations. Imagine that I sit in a laboratory and I want to produce a certain thickness, and I say, okay, I'm going to change the temperature from 800 to 801. Now I'm going to change it to 802. Now I'm going, and then for each one of these, I'm going to do 250 combinations for the pressure. And for each one of these, I'm going to use lubricant A and lubricant B. This is going to be too many to be able to handle. So there are better ways to actually do it than to try all different combinations in this. So this is going to be time consuming and very costly. So what you do here is you design an experiment. And the design of the experiment is like this. You don't take all the data between what did we say, 800 to 900? You don't take all these data. You just take the minimum and you take the maximum. And assuming that there is a linearity in the middle. So here, instead of going into 50,000 combination, all it's asking you is maybe, in this case, only 8. In 8 combinations, you can actually draw a very good conclusion. That's, of course, if it is linearly, you know, because some systems are weird, but in many systems, and you can try it anyway, you might get from 50,000 combinations to 8 combinations. And how did we get the 8? Anybody can think? Why 8?
Actually, this is my question. From where do we get 8?
Yeah, it's 2 to the power 3. You have 3 factors, and it's 2 to the power 3. It means that you're going to try 2 times for factor 1, and for each one, you're going to try 2, and 2 for the third one. So it's 2 times 2 times 2. That's what it means. That's all the combinations. So if we look at them here, for example, this might be easier. These are the low values for the lubricant, and these are the high value for the lubricant. And for each times you put it in low, there are 2 low value for the lower pressure, and there are 2 higher value, and so on. So these basically, you have 2 values, you multiply them by 2, you get 4, you multiply them by 2 again, you get 8. So it's actually 2 to the power 8. It's just like doubling, you know, each time. So it's 2 times 2 times 2. That's if it is full factorial. Full factorial, that means, you know, you're considering all the possible combinations within this concept here. I'm sitting, you just say, I don't have 100 degrees variation. I only have 2 levels, either high or low. So in temperature, I only have high and low. In pressure, I only have high and low. And in lubricant here, anyway, it's only A and B anyway. There isn't more than this. So the total combinations is 2 times 2 times 2 instead of 100 times whatever, 250 times 2. So that's a big reduction in the numbers here. So that's what you do. Here, if you notice here, one important thing when you do design of experiment, you want to have a random sequence. You don't want to have all low at the beginning and then all high at the end for the lubricant, because there are sometimes effects, other effects. Maybe at the beginning the lubricant is hot or cold, so there is a variability with time. So what you want to do, you want to actually put a random sequence here. It will give it to you. The software, the good thing about a software like Minitab, it will give you the standard order. It will give you the run order. That means he wants you to run this one first, then run this one first. This means that if you run this one here, so you're gonna put the temperature low, you're gonna put the pressure high, and you're gonna put the lubricant high. Then what is your next experiment? Your next experiment is this one here. You're gonna put them all low. Your third is no. The first one low, then high, then low. So anyway, these 8 are all the possible combinations that you can think of if you choose just low and high. And then for each one, you're gonna put the output. You measure the thickness. So you're actually going into the laboratory, you're setting up your experiment, you're taking data. So you're setting low, 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 and you're taking a reading. Then you're setting number 3, low, high, low, and you're taking a reading. Then you go to number 4, you're setting high, high, low, and then you take a reading. And once you collect this reading, then you're done with data collection. You're gonna go now to the analysis. You just basically put the data into the software. So that's what it is now here. You just actually put the data in the software. And here the lubricant, you can actually say high, high, low, or you could actually put the temperature as a number and the pressure as a number and the lubricant. And as you can see here, there are only 2 values, either 800 or 900. And there are only 2 values here, either the low one, which is 1750, or the 1500. And from this, you just hit go, and the software will actually give you the analysis. And let's the result of the analysis. And let's look at the result. This is the result here. It's telling you here that factor A, which is the temperature, is the highest factor affecting the thickness, the output thickness. You have B coming next, which is the pressure. And what do you think? This one here?
It's lubricant.
No, it's not lubricant. Lubricant is this. It's C, because we have A.
Combination of temperature and pressure.
Exactly. So it's AB. So you have, and this is a weakness of regression. Regression does not tell you interaction, but design of experiment, it tells you there is one factor which is A, there is a factor which is B, and there is an interaction factor which is basically the interaction of A and B together. And C, which is the lubricant, it really does not have any big effect in this. So it doesn't matter actually if you put lubricant, the first lubricant or the second lubricant, there isn't much. Because here is a threshold value, it will calculate a threshold value, and anything above this threshold value is significant, and anything below this threshold value is not significant. So that's very good piece of information. Only with 8 runs, you gain a lot of information from your system. And this, by the way, is not just for laboratory, for anything. You can think of anything actually to do design of experimental. Of course, if the data and the physics and everything lend itself into coming up with a model, because sometimes it's not easy to come up with a model. Sometimes the factors that you put are not probably the right factors. So with this is now you have a good piece of information. Now you say that, well, I know that C, B, and all of these are not significant. So why should I even include them? Why don't I just go for another set of analysis and ignore basically C basically. Why don't I just use? So, but before I go there, let's look at the analysis of this first one here. And I'm sorry for the quality of the slide. Again, you look at the R square, which is very important, and look at here. You have 98%. This is good number. You say, oh, okay, this model, it's just the quality of the model, because here you're coming up with a mathematical model. You're saying, oh, okay, this mathematical model, I'm very happy with it. I think I'm coming up with conclusions. I'm coming up with result. I have confidence in this. And again, always the p-value. You want to see your p-value low. And as you can see here, p-value is low. That means the temperature and the pressure, and as we said, the temperature and the pressure together are actually like the interaction. So all of these three values, three factors have a low p-value. So I'm now happy that these are the affecting, the contributing basically factors. The other factors, because here are all the 8 basically. All the 8s, they're not really, especially the temperature, pressure, lubricant, the interaction between the 3 is not of high value. So now I say, okay, I'm going to get rid of some of these here. I don't want to take them all. So I'm going to do the analysis again. I'm going to only put A and B this time. And I'll just take the data that I have there. That I don't need to take actually new data. Just the data, but this time I'm only going to use A and B. So I have A and B, and now the analysis is again, they're all above my threshold value, so I'm happy with them. I look at the same result, the data, and now I'm getting 96, which is a good number. I'm getting all zeros as p-value. Now notice I only have now what? I have only 4. I have the temperature, the pressure, and I also have the temperature and the pressure together. Of course, plus a constant value, which has nothing to do with the pressure or temperature. So these are the 4 combinations basically. Plus, what I get, something very important here, is I get an equation. Let's say now I don't want this thickness. I want a specific thickness. I want my machine to produce to me not this thickness. I want another number here. So what you can do, you can just play with these and play with these parameters and see which combination of temperature and pressure will give you the output thickness based on the equation that you got from your analysis. So this is called design of experiment. A design, that meaning you are designing an experiment. You're not just going to trial and error. Let's take this up. Let's take this down. Listen, no. This is a design. You're designing your experiment basically. So what we have talked about so far in the design of experiment is a full factorial, mean that you're taking all the factor, you're taking the low and the high and the low and the high of the other one, and the low and the high of the other one. But what if you actually have let's say you have 8 variables. How many combinations do you think we have? Anybody would like to give a guess? Engineers, I want to hear you.
I think it's 2 to the power 8.
2 to the power 8, exactly. And what's 2 to the power 8? Yeah, I know. 2 to the power 8 is 256. So it's actually 2 times 2 times 2 times 2 times 2 times 2 times 2, 8 times, and that's 256. And if you have 8 factors, even 256 might be too much to handle. So Alain Abdelaziz, منور حبيبي.
الله يسلمك يا دكتور.
حبيبي.
عشان نتفاعل معك، عشان تشوفنا يعني.
ايه احسن، على الاقل نشوف في وجيه معانا، مو قاعد اتكلم مع الشاشه طول الوقت. حلو. That's good. Thank you. Thank you. If these are too many variables, and here is the equation basically, it's 2 to the n, okay? Sometimes because you're doubling every time, this might be so many combination. So what you want to do, maybe by carefully choosing fractions of the trials. Abdul Aziz, you're looking so good, and I'm just keeping looking at you. I think I like the previous way better. So I don't. So disappear, okay, for now. When you have a question, come back. That will be good. Very good. Thank you. So, but by carefully choosing the fractions of trials, you know, you could actually get results without going through all the 258. Oh, sorry, 256, I guess, whatever it is. Okay, combinations. Because the higher order effects, like I want to test the effect of interaction of A, B, C, D, E, all the factors together, that's normally unlikely to be there anyway. So you could actually even run your experiment with lower number of factors. That's so, and actually this is a these are the available designs here. You could choose one of these designs. And the red means it's not too good. The yellow, yeah, it's fine, and the green is good. So if you have two factors, if you have two factors, you have to do full factorial. That means you're gonna need to do 4, 2 to the power 2, basically. If you have 3 factors, then actually you might actually need to do 8 as well, because if you come to 4, you might be losing some information. But if you have 4 factors, then you don't need to go to 16. Maybe you could go to the yellow zone here, and then the yellow zone, the good thing about the yellow zone, it could work, but if it doesn't work, you could use it as screening. You see which one really has an effect and which one doesn't have an effect. So like we did before, maybe 2 or 3 factors are not, I don't need them anyway, so I just throw them away and focus on the most important factor. So that's basically the story about design of experiment. But you're just gonna have to experiment with design of experiment to understand it better. Sometimes we have the cannon, like you have something to throw basically into a target. And if you're going to do projectile motions and mathematical calculations and maybe get a nerd mechanical engineer to calculate for you all this projectile motion, it will take forever to calculate all these equations. But maybe if you just take a few data, and we did this actually, and we were able to take the ball and it will actually go inside the cup. We're actually projecting a ball into a cup, and we didn't know how, what's the angle that we need to set it at, what sort of force that we need to put, and so on. But with a few experimentation, we design an experiment, and at the end we were able to get it exactly where it was. So that's one way to improve performance. Basically, this is actually performance. You want to know what factors will actually affect your performance. So this is one way. And I think for people who work in laboratories, maybe Dr. Hawra as a pharmacist, maybe Dr. Suleiman, maybe Dr. Fayyad. I think there are probably a lot of applications for something like this. And even other things as well. In engineering, there are so many applications. You want to say, because in engineering, you're dealing a lot with the pressure, like in welding, for example. Maybe for those from SPSP, okay? Maybe, and I know some of you are Abdul Aziz, right? I think you're a welding instructor. and you have to do welding a procedure. And the welding a procedure, basically you're changing different parameters, the pressure, the temperature, whatever, the speed of the, and so on. And then you want to get a certain result. So you want to see what is the best combination so you can design your procedure. So this is, and then you'll get your customer happy, because at the end he wants certain specifications for it. Last comments here in the DOE, replications. Sometimes for the same trial, you want to do more than one replicate. This is just to improve basically the confidence. You increase the confidence in the result. So replications is one thing, and sometimes you can actually ask the software, say, I want 2 replications, for example. Blocking, because sometimes you cannot do the whole trial in one day, so you need to do another day to come back to it. And maybe today there is wind, there is other some things, you know, that you want to tell the software that this is a different block. So maybe there is another factor that's coming here or there. Maybe the operator is different, maybe whatever. So you wanna put them in blocks. And also, as we said, you know, the sequence randomization. You need to make it random. You don't want to start all low. You don't want to fix 2 variables and start changing 1 variable one at a time. No, you wanna. It will give you random. The software will give you random. I want you to take this up. I want you to take this down. Now I want you to take this up. Okay. So it will give you a way of adjusting things. So this is an important issue. One last thing in design of experiment, and I know some of you might be interested. I think maybe Dr. Fayyad and maybe Dr. Salman in this. As Taguchi, I know that many of you may it will never be in the exam. This is too details or too advanced. But Taguchi method is the same as design of experiment. It's actually design of experiment, but this is a test for robustness of things. Some factors, they're so sensitive. If you change it a little bit, what will happen? The result, as long as it's fixed at one value, it's fine. But once you change it a little bit, then your result will be thrown away. And then you want to actually make this factor as robust as it can be. And I think I came up with this example today to illustrate, and I think this is a good example. Let's say that this is basically a surface here, and you're putting a ball on this surface. As long as the surface is horizontal, the ball will probably not move either way. But maybe a slight vibration or shake, maybe this is going to throw the whole thing away. So it's good as long as this is set in a certain position. So here, for example, the stability of the ball depends on the inclination angle, the surface roughness. If the surface is rough, then it may not move, and maybe the roundness of the ball, how round it is. But which one is really more as a factor or more affecting the robustness of your model? To say your model, you want to hold this ball stable. So you want to see how much basically you can tolerate. And the more your system is robust, flexible, allowing you tolerant, basically, the more it is tolerant in allowing you to make mistakes. It's not exactly, because it's difficult to make things exactly when you're designing something. Maybe for teeth fixtures and things like this, or orthodontic treatment, sometimes some of these factors, it's not very easy to adjust exactly at a certain value. There's always be, some tolerance there. So you want your system to be robust. So Taguchi will actually tell you which one of these factors Is it the roughness? Is it the inclination angle? Is it the roundness? For example, in this ball, is the more unstabilizing factor, if I want to say. So you can focus on it, and how to make it stable. Basically, that's the purpose of it. So this is the end of analyze phase. The improve and control phase is going to be much easier than in concept, and I think we're going to go very fast in it. But I think it's probably time to take a break, and we'll come back at 8:15. Any questions before we break? And this and the analyze. Either I confused you so much, or I was so clear to a point nobody has a question. No question.
السلام عليكم دكتور.
حياك الله.
الله يحييك. This is موفق.
Please say your name. موفق حبيبي. Yes.
Yeah. Regarding the design of experiment, this is all will be done by the software, right?
Yes, the analysis and the calculation will be done.
Yeah, the analysis, yes.
Yeah. But you need to understand, what factors, what are the minimum, what are the maximum. You also need to go and take the reading. And also you need measurement system analysis. At the end, how accurate is your data? Is Salman Mishari taking your data, or is it Dr. Fayyaz taking your data? Okay, so you want to see, all the measurement systems.
والنعم منكم انتم الاثنين. الله يبارك. Regarding the Taguchi method, يعني how we will decide which factor is more effective?
I don't want to go actually into more details. I'm just saying that there is the Taguchi method. Okay, and it's not going to be, it's not a green belt, to be honest, subject. But I don't want to go into details because it could get very complicated, very deep. But the purpose is that you want to select which factor is actually giving you the more stable, which one you can, how much room can you actually play with one factor without causing you instability in your output, whether you're designing something, you're fitting a fixture, you're making a weld, whatever, because something could actually throw you off just by a little bit. It's only good at this level. Once you change it, the whole thing goes out. But that's all you need to know about it for now.
Yes. So could we say?
Thank you very much.
Thank you. So could we say that the Taguchi method will define the limits? It will give us the limits of inclination angle at which stability will be maintained.
Right. It's just if you set it at this angle, it will be fine. It's just
this range.
Increase it a little bit, and just like when my mother, rahmatullah alayha, she cooks. Okay, she is fine because she knows exactly what she puts. If I come, then it's just a little bit change. I didn't change it much. Just a little bit change. The whole thing, the whole dish goes out of control. So you don't want your system to be like this. You want it to be fault tolerant in a way, because you're giving it to an operator. You're giving your method to whoever designed this. You tell him set it at this angle. What if he is wrong a little bit? So give him some room. Basically, don't say, "Well, I told you exactly at this level." You want your system to be robust. We say that it's about robustness, basically.
Thank you. Very well put across.
Thank you very much. Thank you. So it's 8:10. We'll take 10 minutes. We'll come back at 8:20. Is that good?
Can I ask a small question, Dr. Salman?
Yes. Who's this, please?
This is Jamal Hashim.
حياك الله. أهلا وسهلا.
Thank you. Doctor, regarding DOE, and sorry to be last minute, but regarding the DOE, you said that in order to ensure our data or our analysis is reliable, we gotta do the test more than once, right?
Yeah, replication. Yes, it's
replication.
Confidence. Replication is good. Yes.
Yeah. So when we do that, do we change the what is it called? The order of
replication for each setting. You say, I'm not going to just test it one time. If I put them all low, for example, I put the temperature low, the pressure low, the type A, for example, that's a setting. It's called. That's a try. Okay. I want to take more than one data point. I just don't want to take it just once. I want to take it this will improve the confidence in the data.
Do it change the order of how it is run? يعني,
well, I'm telling you, you just give the software will give you it will give you the design, basically. That's the meaning of design here. It will design it for you. It will tell you, okay, now do this. Now set this at this, set it at this, set it at this, and now take a reading and give it to me. That's what it will give you. So the whole design will actually be done by the software.
Okay, all right, great. Thank you, Doctor.
You're welcome. You're welcome. So let's come back at 8:20, and okay, so we'll be fair for everybody. So I know.